So far, we have talked about the direct methods in solving simultaneous linear equations. Now, let's talk about a bit on iterative methods. Okay, we also call this as indirect method. Um, this method starts with an initial guess of the solution x and then repeatedly improve the solution until the change in x becomes negligible. Okay, so for your sheet work, what are the pros and cons of iterative method over direct methods? So do some research. Obviously, direct methods is more better because you can immediately get your answer, but there are some problems, there are some equations that we really need iterative methods. Okay, but it's beyond the scope of this class and it is in the advanced numerical methods, but here we simply try to understand how it works, how to deal with iterative methods as well as some of its applications. Okay, so we have discussed there are three popular method in iterative method. Let's first discuss Gauss-Seidel. Okay, so for Gauss-Seidel, so remember for the equation or systems of linear equations, we have ax equals to b. Okay, now for iterative methods, so solution x or is already given or guessed. Let's say 1 2 3. Okay, and then verify whether if you multiply a, so we have a coefficient a and b, whether how equal they are. Okay, so you basically, if you multiply this one, these two, this will result to the same matrix as b. Okay, let's say the result will be 3 4 5, let's say, and then the b is 3 1 2. So that's the correct, supposed to be the correct product of that a, that ax. Okay, now so therefore you complete the error and then uh, compute the error, and then with the error modify the new x. Okay, the error, modify the new x. Okay, then the new x, the next the iteration 2, so then you multiply ax equal to b, so another ax prime. Okay, so the new x, and then you check again. So what will be the result of this? Let's say b prime is equal to b, really, and then you will get the error, and then modify x. Okay, so that's the process, and then so on and so forth. Okay, now in Gauss-Seidel, we start choosing the starting vector x. If a good guess for the solution is not available, x can be chosen randomly. Okay, then the iterative scheme looks like this. So you have here the x prime, okay, the next I, and so you have here the change. So you see the difference between the bi, we have demonstrated that one. It's actually here from this side. The error is like we have here b, and then here we can say this is the b asterisk. Okay, b asterisk, so therefore b minus b asterisk, so this will be your error. Okay, so for sure there's a difference in that, no? Especially if we can't get the correct guess. Okay, so then we can yeah, so here, so you get this x, okay, is used to compute each element of x, always using the latest available values of xj. Okay, so xj is the here we have xj is the latest available. So in this case we have x prime. For this example, we have the x prime. We use x prime in this equation. Okay, so then we get the new x. Actually, this one is the answer for this one is actually the 1 over a. Sorry, then b minus a x prime. Okay, so basically the x here, and then we'll update. We call this the update. Okay, updating the new x with the new x, old x. Okay, if you multiply that one. Okay, now so it's clear, but we can use corresponding iterative method with relaxation. So relaxation is when you have to put a so-called here, we call this one the optimal value, so predefined threshold. Okay, so which is an optimal. So if the difference between if the difference of let's say the error reaches, okay, a certain threshold, then you can stop already. Okay, so and then um, so W here is simply like a how you call this, it's like the relaxation, meaning it's like the speed of getting the closer to the correct answer. So how fast your iteration, not the speed of computation, but it is the speed of going to the correct answer. It's like if you're looking for, if this is your graph, and then this is the line of the correct answer, or the getting error. Let's say this is error, and the speed, no, of getting to this point. Okay, so maybe like that, or you might as well go straight, no. But the problem with going straight is you might have a you may not be able to get the correct one. So basically a good approximate of your W until it reaches here. Okay, so W is just simply a relaxation such that you will not okay, so another example here, if your solution is in the bottom of this one. Okay, so if this is your initial value for your x, and then you will have a very fast W. W is high, it becomes like this, then like that, no. But sometimes it will go diverge. Okay, so there's a possibility of divergence. Now if you have x very slow, sorry, the W is very slow. Okay, so what if your W is very slow? What will happen is that you have a very slow, okay, so it will change like that. Okay, it will flow very slow until it reaches in the bottom. Okay, so basically, so to give you a better drawing, so it goes like this. Okay, first point, second point, third point, fourth point, 5 point, 6 point. Okay, when your W is equal a bit lower. Now if very low, so maybe it will go that very slow. Okay, so W should have an optimum value. Now there's no practical method of getting the optimal value of your W, but you can use this one. Okay, so this is an approximation of the value using the given value of your x. Okay, so you can update also it's like the speed, no, the W. So this is the overall procedure of the pseudocode carrier. So with iteration, W equals to 1, and K is the number of iterations. So most of the time they use number 10 because most of the problems can be solved in at least around 10 iterations. So, I mean, you will get a sufficient value. Okay, so I mean, if your correct answer should if your answer, the solution, let's say one of the value is 3.14, 16, 17, no, 20, then your answer, your estimate using the iterative method is 3.14, 16, let's say 3.16200. For example, this is your answer. Now the difference between them is very small. Okay, this is around you have 16, 2, so you have 3, 0, 0, so around 1, 2, 3, 4, 5. Okay, so this is the error, and you see it's very small and it's not so significant for us. Then you might as well use this value, no? Although in reality you may not be able to get this correct value, no. So but using the approximate, using the iterative method, you might be able to get a approximate value. Okay. And then if you would like to round this off, let's say round this off at in the 4 digit here, so you will have the same value, right? Okay, so that's the beauty of um, approximation. Okay, so we have these k iterations, record the k x, I mean the 10, in this case 10 change of x. Okay, so here we say that we can stop the iteration if this one the error is, let's say, 1 times 10 to the negative 6. So for example here, the error here is 1. So if you it already reaches 0.00001, so the e here is lower than the threshold. So if this is your threshold and your e is this one, then you have a correct, you can stop the iteration. Okay, you can do that. Instead of identifying the number of k, you can as well lower the threshold. Okay, so then compute optimum, then perform subsequent iteration. So we update also the weight. Okay, so we update the relaxation in this case. Okay, so using this formula, so we have here the code for our Gauss-Seidel. So just like to we have the omega here, which is initially equals to 1, and it will also be updated later. So here, this is the formula here, the update. And then we have k10. You might as well put it 100, and then you can stop as many as you can. Okay, so here we have I in the range of 500. So I think here the iteration is 500. Okay, so but it will stop at 10. Okay, so if I is equal to 10, then we have here. Okay, so this is like you have the range 1 to 500, but actually you can stop at 10. What you can do is you just remove this one and then put 10 here. Not a problem, but you will be using the value of your k, so you might as well do that. Okay, anyway, so here, okay, so very simple iter equations, kx, so here we have the iter, we need this function. Okay, so let me find the iter equation, right? Anyway, so this is a function. Okay, so which will be defined later. So you have here iter equation, so we will just use that one. We will explain that one later. Okay, so but actually this is just the update, this one, the update equation. Okay, so here this one is just the overall, it's like a general procedure of the Gauss-Seidel, and the formula for the this one for the relaxation will be on the iter equation. So it's just this is a very good one because you can see where to place the function within a function, so that it will be easier to classify. It will be easier to put order in your code. Okay. Okay. So we have defined Gauss-Seidel. Now another method is what we call conjugate gradient method. Okay. So this is actually from a minimization problem of a somehow like a quadratic equation. You can see because you have 2x, meaning x squared. Okay, and it's quite popular in math. Okay, so when the gradient may so sorry, another popular method, it is simply a minimization problem of scalar value. So okay, so actually that's from this formula. So let me go into another code here. So this is actually a Anyway, so later let's discuss that one. In math, when the gradient function f, which is ax minus b, is 0, that is ax minus b is equal to 0, f is minimized. Thus, we have the simultaneous equation here, ax minus, this should be ax equals b. Sorry, it should be ax equals b. Okay, so that's it. So we have a simultaneous equation, ax equals b. So in math, we know that the gradient of a function f, whatever it is, if it is equal to 0, okay, so take note of this. Actually, this one is a quadratic, no? So we have 1 half xt ax minus bx is equal to 0. So because the gradient, I think if I'm not mistaken, the gradient of a, it's like that, I forgot that. Okay, so grad, no? So the grad of f is equal to 0, then you have f is minimized, f is minimum. Okay, so in that case, we can also apply that one in the linear equation. So if this is equal to 0, so you divide both sides, everything by x, so cancel one of the x, and then also 1x over 2, cancel 1 half the other side, and or maybe the 1 half here will be included in the a, no problem, so you can cancel one of the x, cancel one of the x, and yeah, so you have your ax minus b equals 0, so you have ax plus. Okay, so you have a very simple linear equation. So transpose, so you just transpose. Sorry, we have bt. I got confused. Sorry, this is bt, and this is equal to 0. You can transpose this one. Okay, another way of looking at it. So I think I made a mistake on that. So axt ax. So if you transpose these two equations, it becomes bxt. Okay, so you have xt ax. Then if you multiply both sides by x, okay, so let's say like that. Now another x here. So this becomes identity matrix b. Okay, xt times x, and then in the other side I. And you know that identity matrix, any matrix, let's say b matrix times I is equal to b. Okay, because any number multiplied by 1 is equal to a number, the number. So this is therefore equal ax equals b. Okay, so that is how it goes. So then the minimization problem using the iteration is performed. This is summarized by the following pseudocode. So very important here. Okay, the getting the gradient of this one, we can get the value for your x. So I will not further explain this because this will be part of another topic for not in the linear, in non-linear subjects, no? So I think in the other modules. So this is the general pseudocode. You have this one first, and then you assign a value r, and then you have the steepest descent. So we will talk about more on this in the separate topic. I'd like you to just simply get the essence of this class. No? Okay, so this is part of the script. Okay, so this linear programming convex optimization course. It is rather important to understand the essentials. Okay, so how to differentiate the two. So basically here the idea is to how you call this, you have still the iterations. Okay, you have this one, you get the alpha is the how you call this, I forgot, the constant, so this is like the speed. Okay, and then you multiply with s, and then basically this is just simply the idea earlier. If you have the same, if you have the same position, then you have your initial x, and then you will go here. Okay, you will go here, go here. Okay, so this is when you have alpha. So I think the alpha is the coefficient of descent or something like that. Okay, um, we'll further explain that one later until you reach x. Now, if you increase alpha, then it will go unsteady, and then it might diverge. No, diverge is divergent is going away from the solution. Okay, so we need to have a convergence is going into the solution. Okay, going toward the solution. So okay, so we have this formula here. Okay, so basically uh, yeah, so we'll explain this one in the other modules, but the idea is simply minimizing this one, and then if it is close to 0, then we are almost with the correct if this is equal to 0, then x is close to the actual or correct or exact value of x. Okay, but we can stop it using some of the error tolerance E. Okay, so if r, okay, it's r is like the difference between the previous and the present b. Okay, because b, this one is the present b, and then this is the original b or the given b. If this is very big or this is below the tolerance, then we can stop, and then we assign the value of your bk to for your bk, and then you have sk. Okay, and yep, so this is for the code of conjugate gradient. Okay, and so let's try some example. Okay, so we have here matrix A. Okay, so for -1. So if I'm not mistaken, this is in the previous examples in the direct method, so you can as well verify that one. Okay, now using Gauss-Seidel, so we have the iterations. Okay, and then this is the equation of the Gauss-Seidel, and then do some iteration, and then we have here. So how many equations do we need? So there are 20. Okay, so here number of iterations 259, the relaxation factor is 1.75, and then we have this solution. Okay, so the solution for our x is this one. Okay, so sorry, I think I made a mistake. It should be 4. Yeah, that's right. So 1, 2, 3, 4, 5. Actually, I think this is, let's see, iteration x, np0n. Oh, sorry, I think I made a mistake. So it should be um, n. How many n is this? 3. Let's say 3. Number of iteration. Sorry, this should be 3 times 3, 9. Oops. How come this is? Wait. Let me check. I think we haven't run the A and B. We haven't encoded them. Sorry, I think yeah, I think there's a mistake here. I think sorry, this one is for the omega. If you want to get omega, 9 omegas, so you have these values for your omega. Okay, so but this is not yet the answer for A to find the x. Okay, so because we're not using A and B, and then using the conjugate gradient method, so we have ax, we created another function. Ax is simply getting into the formula here, and actually we have um, actually this is just simply a how you call this, this part here. You can ax this one here. Let's see. Actually, it only defines the value of your a and x. A, okay, so it's just a I mean, if you have a a vector v, and then to generate, this is just a generation of to generate the coefficient matrix. Okay, so yeah, and then here we have how many equations do we need. Okay, and then from the equations, for example, let's say three equations. Okay, so the solution is that one. So you have here okay, so the ax, then x, and then you have the b. So this will just simply call the ax, which is this one here, and we have the x, then put it in the conjugate matrix. So then you will get the solution. Okay, three equations meaning three functions. So it's only one iteration in this case. Okay. So well, let's try really definite. This one is just simply to get the relaxation factor in this case, and then also the some random. So this one is the one ax inside, no? So it's a generation. So it's not yet clear in this formula. But let's try this one. So with the b, because the previous one actually we didn't use this one here. Okay, so this is the actual another example. Okay, using Gauss-Seidel. So we have encoded A and B inside, and then here is the equation, if you can remember. Okay, so the update solution. Okay, so you can return x. Okay, then using the Gauss-Seidel, so you remember this equation here, and then if you reach the tolerance, so as I said earlier, so you can make it 5 or make it 10. Okay, so then if you reach tolerance, what is our tolerance here? I think okay, the tolerance is 0.1. Okay, so let's see if this works. Okay, so that's a function, and then x is np0 is 3, and then so you have iter equations here. So you have 3 by 3, and then we can run this one. Oops, sorry, there's a mistake. Because omega. Okay, because we need omega here. Iter equation. We haven't run this one. Sorry, should have run this one. Then this one. Okay, that's it. So we have the first iteration, second, third, fourth, and actually on the fourth, instead of 5, actually this is 5, right? But at 4, the tolerance is lower. Okay, I mean the answer is lower than 0.1. So we stop there. So if we increase this one like 0 and then increase the iteration to 10, so we can sorry, 20 anyway, so it will stop somewhere. Okay, it stops at 5th iterations. Okay, so basically the tolerance is, if we put it a bit lower again, okay, so you see it becomes 7. Okay, so the value here is more uh, the significant figures also increases. But if you notice, this one is 3, this one is 1, this one is 1. If you round them off, okay. Now if you make it very very accurate, no, like maybe higher, of course the iteration might exceed 20. Okay, you see the iteration is almost okay 0.99999. Okay, so it's if you subtract it from the actual one, so So the value is less than this. Okay, so that's it. So we have the Gauss-Seidel. Now this is for your um, sheet work using the conjugate gradient functions to solve the following. Okay, so maybe we haven't shown to you the actual conjugate matrix, so it's a bit challenging. So maybe I will use the Gauss-Seidel instead of the conjugate gradient. So we will explain conjugate gradient in some other topic. Okay, so Gauss-Seidel. Seidel method can do the following. Okay, so you just basically copy this one, okay, and then run on your own and solve the following equation, and make sure that your tolerance is reasonable. Okay, and that's it. So thank you so much for attending this course, this class. See you next time.